Hello, Bachon. Welcome to the class. Today, we are going to study a very important topic from your Unit 10, Wave Optics. Now, the name sounds a little heavy, I know. Coherent and incoherent addition of waves. But trust me, we're going to break it down so simply, you'll wonder why it ever seemed difficult.
You know, this one concept is actually the key to understanding bigger topics like interference and diffraction. So many students get stuck here. But after today's session, I promise, you'll have zero fear and you'll be absolutely ready for your exams. So, tension met low. Let's begin. Okay, so let's start with a little puzzle. Just think about this for a second. You switch on a 100-watt bulb in a room and you get some brightness, right? Now, what if you switch on another identical 100-watt bulb right next to it? Logically, the wall should just become twice as bright everywhere, shouldn't it? But it doesn't. Any idea why? Just keep that question in the back of your mind. We're going to find the answer together. Well, the answer to that little bulb puzzle isn't found by thinking of light as tiny particles. Nope. The whole secret is in understanding that light behaves like a wave. And it's all about how these waves work together or, well, how they don't work together. It's all about teamwork. The best way to picture this is to imagine a perfectly still pond. Now, you throw two small stones in side by side. What happens? You get these beautiful circular ripples, right? And when these ripples meet, something magical happens. Where the top of one ripple meets the top of another, the wave gets even bigger. But where the top of one ripple meets the bottom or the trough of another, poof, the water goes flat. They just cancel each other out. And believe it or not, light waves do exactly the same thing. So let's look at the first case. When two light waves are live at a point and they are perfectly in step, we say they are in phase. This means their crests line up with crests and troughs line up with troughs. It's like they're helping each other, pushing and pulling at the same time. The result? They build each other up to create a much brighter spot of light. This perfect teamwork is what we call constructive interference. You can think of them as being good friends. But what if the opposite happens? What if the waves arrive completely out of step? So a crest from one wave meets a trough from the other. Now they're working against each other. One is pushing up while the other is pulling down. And what happens? They completely cancel each other out. And from two sources of light, you get darkness. Nothing. This is called destructive interference. In this case, they've become enemies. So you see, the whole game, the decider between bright and dark, is this one thing called phase difference. Don't let the name scare you. It's just a way to measure exactly how out of sync two waves are. We give it the symbol phi, and this single value tells us everything we need to know. Will the waves be friends, enemies, or something in between? The phase difference has the answer. All right, so now that we've got the feel of the concept, let's switch gears a bit. We need to learn the official language, the exact definitions from your NCERT textbook. This is super important because using this exact wording is what gets you full marks in your exams. So pay close attention now. So what are coherent sources? Let's look at the official definition. Two sources are said to be coherent if the phase difference between the waves they produce does not change with time. The key words here, the absolute most important part, is does not change with time. It means they have a constant phase difference. Think about it. If two waves start out as friends, they stay friends forever. If they start as enemies, they stay enemies forever. Their relationship is stable, it's predictable. That's what makes a source coherent. And this comparison makes it crystal clear. Coherent sources, with their constant phase difference, are like two singers hitting every note perfectly in sync. What you hear is a beautiful, stable pattern of loud and soft music. But incoherent sources, their phase difference is changing randomly all the time. They're like two singers singing the same song, but one starts late, the other speeds up. It's a total mess. There's no stable pattern. All you hear is just the average loudness. And the master rule behind all of this teamwork, or lack of it, is something called the superposition principle. It sounds fancy, but it's really simple. It just says that if you want to find out what happens when many waves meet at a single point, you just add up what each individual wave would have done at that point. That's it. It's the fundamental rulebook for how all waves interact. Okay, let's get into the maths a little bit. Don't worry, it's very straightforward. Now that we understand the ideas, we can write down the exact conditions, the specific rules, for when waves will become permanent friends to give us brightness, and when they'll be permanent enemies to give us darkness. This is what you'll need for solving all the numerical problems. So for constructive interference, that means a bright spot, the condition is very simple. The difference in the path traveled by the two waves must be a whole number, like 0, 1, 2, 3 times the wavelength lambda, so n lambda. This condition automatically makes their phase difference an even multiple of pi, 0, 2 pi, 4 pi, and so on. And when this happens, the intensity is maximum. It becomes 4 times the intensity of a single source. And for destructive interference, for a dark spot, the condition is just a little different. Here, the path difference has to be a half-integer multiple of the wavelength. So something like half a lambda, 1.5 lambda, 2.5. You get the idea. This makes the waves perfectly out of sync, with a phase difference of pi, 3 pi, 5 pi. And the result? The intensity becomes 0. Total darkness. Complete cancellation. Now, here it is, the master formula. This one equation is like a treasure chest. It can solve almost any problem in this chapter. The resultant intensity, I, at any point, is equal to 4 times the single source intensity, I naught, times cosquared of the phase difference, phi, divided by 2. Why is this so powerful? Because it works for any phase difference, not just for perfect bright or perfect dark spots, but for everything in between. Chilo, let's test it out with a very simple example. What would be the intensity if the phase difference, phi, is not 0 or pi, but right in the middle, say pi by 2? Let's find out. Okay, so we just take our master formula. We put phi equals pi by 2. So we need cos square of pi by 2 divided by 2, which is pi by 4. Now what is cos of pi by 4? You know this, it's 1 by root 2. We have to square that, so we get 1 by 2. Finally, we have 4i naught times 1 by 2, which gives us 2i naught. Ekdam simple. So in this case, the final intensity is just the simple sum of the two individual intensities. Okay, bachcho, listen very carefully now. This next part is extremely important. I call this the silent killer mistake. Why? Because it's a very simple misunderstanding, but it's one that silently eats away your marks in the board exams if you're not careful. So let's go all the way back to our very first question. We're finally ready to give it a proper scientific answer. Why on earth don't those 200-watt bulbs just make the wall 200 watts bright? The common trap, the wrong idea that feels so right, is to think that you can just add intensities. I total equals I1 plus I2. I mean, it makes sense in our daily lives, right? But in the world of wave optics, this simple addition is almost always wrong. And here is the correct answer. Two separate light bulbs are fundamentally incoherent sources. You see, the millions of atoms inside one bulb are emitting light completely independently of the atoms in the other bulb. This means the phase difference between the waves from the two bulbs is changing randomly, millions and millions of times every second. The bright and dark spots are flickering so incredibly fast that our eyes can't see them. All our eyes can register is the average brightness over time, which it turns out is simply I1 plus I2. So the intensities only appear to add up because the sources are incoherent. Whew! So we've solved the puzzle. Now let's just take a moment to connect all these dots. We'll see how this helps us in the next section, and I'll give you a quick summary of everything you need to remember for your exams. Now you might be wondering, sir, why did we spend so much time just on this one idea? Well, it's because this concept of coherent and incoherent addition, it is the absolute foundation for everything that comes next. Young's double-slit experiment, diffraction, it all builds on this. If you have truly mastered this topic today, believe me, the rest of the chapter is going to feel like a piece of cake. And finally, here is your one-page summary. Take a screenshot of this. This is your revision gold. Point 1, coherent sources have a constant phase difference and give a stable interference pattern. Point 2, incoherent sources have a random phase difference, so their intensities just add up on average. 3, for a bright spot, path difference is n lambda. 4, for a dark spot, path difference is n plus half lambda. And finally, the master formula for intensity is I equals 4i naught cosquared phi by 2. If you remember these 5 points, you will never, ever have a problem with this topic again.